Welcome to today's paper reading. Today's paper is titled, Retrieval Augmented Generation or Long Context LLMs? A Comprehensive Study and Hybrid Approach. This paper was published on the AR14 preprint by Zhuowan Li and colleagues from Google DeepMind and the University of Michigan. In this study, we compare Retrieval Augmented Generation, RAG, with long context, LC, large language models, LLMs, like Gemini-1.5 and GPT-4. We benchmark these models across various datasets, finding that LC LLMs generally perform better when adequately resourced. However, RAG's cost advantage is significant. To balance performance and cost, we introduce self-route, a method that uses model self-reflection to route queries to either RAG or LC. This approach reduces computational costs while maintaining performance levels comparable to LC LLMs. Our findings offer a practical guideline for applying RAG and LC LLMs in long context scenarios. The introduction of this paper discusses the comparison between Retrieval Augmented Generation, RAG, and long context, LC, large language models, LLMs. RAG is highlighted for its efficiency and cost-effectiveness in leveraging external knowledge, while LC LLMs like Gemini and GPT-4 demonstrate exceptional capabilities in understanding long contexts. The need for a systematic comparison arises due to the contrasting strengths of these approaches. The paper finds that LC LLMs consistently outperform RAG in most settings, but RAG remains relevant due to its significantly lower computational costs. The authors propose self-route, a method that routes queries to either RAG or LC based on model self-reflection, achieving cost reductions of up to 65% for certain models while maintaining performance comparable to LC LLMs. Figure 1 illustrates the contrast between long context LLMs, LC, and Retrieval Augmented Generation, RAG, in terms of long context understanding and cost efficiency. While LC models demonstrate superior performance in comprehending lengthy contexts, RAG stands out for its significantly lower operational costs. The proposed self-route method effectively integrates the strengths of both approaches, achieving performance levels comparable to LC models while substantially reducing costs. In the realm of long context language models, there have been significant efforts to enable models to handle extended contexts. Recent models such as Gemini-1.5, GPT-4, and Claude 3 have achieved larger context windows, but the computational cost remains high. To address this, methods like prompt compression, model distillation, and LLM cascading have been proposed to reduce costs. On the other hand, Retrieval Augmented Generation, RAG, has proven effective in enhancing language models with external knowledge, performing well in tasks like language modeling and question answering with a lower computational cost. Recent advancements in RAG include augmentations with correction, critique, and verification, making the retrieval system easier to set up and host on the customer side. In this section, we discuss the benchmarking of Retrieval Augmented Generation, RAG, versus long context, LC models. We evaluate these models on a subset of datasets from Long Bench and Infinity Bench, focusing on English, real, and query-based tasks. The models evaluated include Gemini 1.5 Pro, GPT-4o, and GPT 3.5 Turbo, with two retrievers, Contriever and Dragon, used to manage long contexts. The benchmarking results show that LC consistently outperforms RAG across the datasets, with significant margins for the more recent models. However, RAG shows better performance on the longer datasets from Infinity Bench, indicating its effectiveness when the input text exceeds the model's context window size. The self-route method is designed to combine the strengths of RAG and long context LLMs, LC, to reduce computational costs while maintaining performance. It consists of two main steps: the RAG enroute step and the long context prediction step. In the first step, the LLM is prompted to predict whether a query is answerable based on the provided context, similar to standard RAG but with the added option to decline answering if the query cannot be answered. For answerable queries, the RAG prediction is accepted as the final answer. For unanswerable queries, the full context is provided to the long context LLMs for the final prediction. Our results show that 82% of queries can be solved by the RAG route step alone, with only a small portion requiring the long context prediction step. This approach significantly reduces the number of tokens used, which translates to substantial cost savings due to the quadratic relationship between token count and computation cost in transformer-based LLMs. This method achieves performance comparable to LC, demonstrating its effectiveness in balancing performance and cost efficiency. Figure 2 illustrates the distribution of the differences in prediction scores between RAG and LC models, scaled to a range of 1 to 100. Notably, 63% of the queries show exactly identical predictions, and 70% of the queries have a score difference of less than 10, indicating a high degree of similarity in both correct and incorrect predictions between the two models. Table 1 presents the results of 3 models, Gemini-1.5 Pro, GPT-3.5 Turbo, and GPT-4o, using the Contriever Retriever. The table highlights that LC consistently outperforms RAG in terms of performance. Interestingly, self-route achieves performance comparable to LC while using significantly fewer tokens. This suggests that self-route is an efficient method for reducing computational costs without sacrificing overall performance. In this analysis, we explore the impact of the top K retrieval parameter on both performance and cost. As K increases, the performance of both RAG and self-route improves, but the cost for self-route reaches a minimum at K equals 5. The optimal K value can vary depending on the dataset, with K equals 5 generally providing the lowest cost. We also examine why RAG fails in certain scenarios, identifying 4 main reasons: the need for multi-step reasoning, handling general or complex queries, and understanding implicit context. Additionally, we discussed the limitations of synthetic data in evaluating model performance, using the Pasky dataset as an example where RAG's performance can be highly variable based on the nature of the query. Figure 3 illustrates the trade-off between model performance and token usage as a function of K. For both RAG and self-route, increasing K leads to better performance as more chunks are fed into the LLMs, gradually improving performance to approach LC. Notably, self-route shows significant advantage for smaller K, such as when K equals 1, where RAG achieves 20.24% while self-route achieves 37.9%. However, the cost trend for self-route is not monotonous. It reaches its minimum at K equals 5, indicating that while the cost of RAG increases with K, more queries are routed to RAG from LC, potentially reducing overall costs. The optimal K varies depending on the dataset and task, suggesting that future research should explore different K values for various applications. Table 2 presents the results of Gemini 1.5 Pro when using the Dragon Retriever. The table compares the performance metrics of Gemini 1.5 Pro with LC, RAG, and a combined method across various datasets. It also includes statistics on token ratios, providing a comprehensive view of the retriever's effectiveness. The data highlights the strengths and weaknesses of each method, offering insights into their respective performances. In this paper, the authors present a detailed comparison between RAG and LC, emphasizing the trade-offs between performance and computational cost. LC shows superior performance in understanding long contexts, while RAG remains cost-effective and advantageous for inputs that exceed the model's context window size. The proposed dynamic routing method effectively integrates the strengths of both RAG and LC, achieving LC-level performance at a reduced cost. The failure analysis of RAG highlights common challenges such as multi-hop reasoning and implicit queries in long stories, suggesting areas for future improvement. Potential enhancements include incorporating chain of thought for multi-step questions and revisiting query expansion techniques for complex queries. The findings are generalizable across different retrievers, indicating the broader applicability of the research. Figure 4 illustrates the distribution of failure reasons for Retrieval Augmented Generation, RAG, across various datasets. The figure categorizes failure reasons into 4 main types: multi-hop reasoning, implicit queries, general queries, and others. Notably, datasets like HotpotQA, 2WikiumQA, and Musique, which require multi-step retrieval, shows significant challenges for RAG, indicated by the blue bars. In contrast, narrative QA, with its long stories and dialogues, faces issues with implicit queries that demand a deep understanding of the entire context, as shown in green. Additionally, QMSum, a summarization dataset with open-ended questions, experiences failures primarily due to general queries, highlighted in red. The other category includes multi-step questions with ambiguities, which are particularly difficult to answer. This analysis suggests potential areas for improving RAG, such as integrating chain-of-thought reasoning for multi-step questions and refining query understanding techniques for general and complex queries. Thank you for watching.